guys, good morning to all of you. Welcome to another session, and in today's session we'll be discussing interference, and this is the first part of interference. I think it will take 2 sessions to complete this interference topic. And from electromagnetic theory we have covered the significant portion already. Only few advanced topics are left, like interference, diffraction, polarization, waveguides, radiations and all. So these topics we'll cover first, and later on, if time permits, we'll go for the remaining topics. So before I start, let me know if everything is all right, so that we can start the session. सारी चीजें सही है कि नहीं बता दो भाई. Very good to go. Okay, so let's start with the basic concept of interference. Interference you must have already learned in class 11-12. Good morning, Harry. Look, interference, what do you understand by interference? When two waves of same frequency, this being same frequency is very much necessary to be coherent. For interference, one criteria is that the two waves which are interfering, they must be coherent, and being coherent means they must be having same. When the two waves of the same frequency travel in approximately the same direction have a constant phase difference. The phase difference may be 0 or it may be constant value may be 0. The two waves, they should be having same frequency and have a constant phase difference between them. Then the resultant intensity of the light is not distributed uniformly. Uniformly means what? Uniformly means, let's say it is like this. This is the uniform distribution. The light does not distribute uniformly. Rather, how it gets distributed? It is distributed as a pattern of bright and dark. How? If I consider it in this way, the pattern goes like bright and dark. Okay, you can understand how it is. Bright, dark, and so on. So in this way, this non-uniform distribution of light intensity is because of the superposition of two. This term is important. Superposition of two waves. This phenomenon has interference. At some points, the intensity is maximum, which are called maxima, or that will give you bright fringe, and interference at this point are called constructive interference. Terms are, I think you are all aware of. The intensity is minimum, possibly even 0. Minimum does not mean always 0 is a special case. Minimum means there may be some intensity, but that is also called minima. For ideal case, when the intensity of the two interfering beams are equal, then only you will get a 0. Otherwise, you may not get a 0. And the interference at this point called destructive interference, that will give rise to dark fringes. Usually, when two light waves are made to interfere, we get alternate dark and bright bands of a regular or irregular shape. So here one example you have been seeing. See, this is one wave is interfering with another wave, and you see when the crest is superimposing with the crest of this, trough is superimposing with the trough of this, you get constructive interference. And as you can see, it is a constant phase difference. So what is the phase difference? Here phase difference is, so in constant phase difference, 0 phase difference is also included. Okay, there may be 0 phase difference or some finite phase difference. So in one sentence we can say it should be having a constant phase difference. Here you can see there is no phase difference, and here you can see the crest, these high points are called crest and the low points are called trough. The crest of this wave is superimposing with the trough of the other wave, and as a result this is giving rise to a dark band. Okay, now the best experiment to showcase this interference phenomena is the Young's double slit experiment. This is the experimental, this gives the experimental validation to this interference phenomena. So you can see in this figure schematically this interference phenomena has been shown. So you have taken a broad source, the sunlight. Now from this broad source, with the help of a single slit, not slit, SLIT, filled with two slits. The separation between the two slits, you see, it is looking like big. These slits may look like big, but let me tell you what is the approximate value of this slit width. Okay, this is separation between the slits. It is less than 1 millimeter. Less than a millimeter. So you can imagine how closely they are placed. We'll talk about it. And as you can see, this give rise, if you hold a screen at some distance d, you get an alternative pattern of bright and dark fields. The central point will be maxima, and around it there will be a regular or consecutive repetition of bright and dark fields. So you can see in this figure, this is the intensity distribution. The maxima corresponds to the bright fringe and the minima corresponds to the dark fringe. So this is a very rough picture of Young's double slit experiment. Now interference can be observed by two possible mechanisms. One is interference by division of amplitude, another one is the interference by division of wavefront. So this here, as you can see, these are called wavefronts, right? You know, these are called wavefronts. So these wavefronts are coming. Spherical wavefronts, a broad source, spherical source. So spherical wavefronts are coming. Wavefronts are getting, here you can see, divided. Again, it is producing secondary wavelets. These are called wavelets. And from here, wavefronts are superimposed. As it goes, the wavefront size increases like this, and for this source also two sources are there. So in this way they goes and they superimpose and give rise to this bright and dark. So this Young's double slit experiment is a demonstration of interference by division of a wavefront. Interference by division of wavefront. Now division of amplitude we'll also talk about when we'll be talking about the parallel thin film. Okay, let me just give you a brief idea. So when you will be discussing the parallel thin films, then at that time we will be talking about this division of amplitude. So a light wave will be incident, it will get reflected and it will get refracted, and from this surface it will get reflected again and it will get transmitted. Okay, some portion of it. So you can see the amplitude is getting divided into different parts. So further, multiple reflection will be there. Okay, multiple reflection will be there. So what? So we will get reflection from the reflected wave, and we will also get reflection from this transmitted. So this is an example of division of amplitude. Okay, in Newton's ring also we get the phenomenon of division of amplitude. Young's double slit experiment is a demonstration of interference by division of wavefront. Understood? So let us go for the theory of interference. The interference is basically the superposition of two waves. The two waves, what are these phenomena? Look, these two waves must be coherent waves. Coherent waves will be following two main phenomena. Coherent waves, what is the criteria? Number one, it should be having same frequency. Number two, constant or zero phase difference. Constant phase difference. These are the two criteria a coherent source must be followed. Now, to produce two coherent source, we cannot produce two coherent source from two sources. We can produce two coherent source from a single source. So there is a basic physical reason why it is, because if you take two sources, their phase relationships does not remain constant. They are constantly changing. So it is not possible to get two waves, two sources from two different sources with constant phase difference. But if you take one source, and from that one source if we can produce two coherent source, it is possible, because whatever changes will be there in the main source, the same kind of change will be reflected to both the coherent sources, and that is why they will maintain a constant phase difference. And since they are being produced from the same source, they will also maintain the same frequency. That is why to produce coherent light source, we need single source. With multiple source, it is not possible. Did you understand this reason? Not. If anyone has any question, you can ask. So let us go for the theory of interference. Superposition of light wave. Okay, very good. Look, first of all, as I have already discussed, interference is based on the superposition principle. Okay, so we are considering let us consider the superposition of two wave trains which have same frequency omega and a phase difference of, look, wave trains, let me just talk. So from wave, from a particular source, let's say some kind of wave is being generated, okay. So if it maintains a constant phase relationship, so it is going like this. So you can imagine it like it will continue in this way. So if you consider this peak to peak distance, this gives you the measure of lambda, right? Peak to peak distance. So whenever we are meaning n lambda, what does it mean? N such units are being repeated, right? N such being is repeated. You can see from this to this is one unit, and this overall thing is wave train, and this is a particular wavelength. N lambda means n number of such units are repeating. Now if the n value is very large, so if we have n plus 1 into so if we just extract one such unit, there will be no effect on the interference pattern. So sometimes we will write n plus 1 into lambda, approximately n lambda, okay. Now you see it is maintaining a constant pattern in this way. Now let's say after some time it is not maintaining a pattern like this, it becomes like this. So from this we can conclude that there must have some change in the source, and because of that it has lost its regular pattern, okay. So for coherence light source, that doesn't happen. We have considered superposition of two waveframes which have same frequency and a phase difference delta. Now let's say if E1 is the electric field and E2, whenever we consider light is an electromagnetic wave. An electromagnetic wave is mainly represented by its electric field, because in electromagnetic field both electric field and magnetic fields are there, but the portion of electric field is too high as compared to magnetic field. Whenever we are talking about electromagnetic field, we are mainly talking about electric field, okay. If E1 and E2 see the electric field components, two waves having amplitude, let's say E01 and E02 respectively, then we can write, you see, E1 is equals to E01 sin omega t. Now we are using a vector sign, so you can give a vector sign here. And next wave E2, it is having amplitude E02 sin, the frequency is same, it must have omega t and a constant and a phase difference of delta, so plus delta, let's call it 1, let's call it. So as per according to the superposition principle of superposition or superposition, principle of superposition, the resultant displacement. These are basically represent displacement, right? And square of this represents the intensity. So you can imagine for the time being that two waves, one is this E1 is going, another wave E2, they are interfering, and we are producing, we are observing a point P. Let's say here we are observing the resultant displacement. Because of E1 there will be some contribution, because of E2 there will be some contribution, and we are taking the vector sum. In principle of superposition we need to take the vector sum. The resultant displacement at any instant will be equal to the vector sum of the individual waves. So let's take the vector sum. ER is the resultant. This will be equals to E1 plus E2 vector sum. Now for our convenience, let's you see this E1 and E2 are very close together, very close to each other. So we can modify this figure. Okay. So if I consider that both these waves are moving in the same direction, then it will also be valid. If the superimposing waves are moving in the same direction, we can eliminate the vectors. So if they are moving along the same direction, then it is just adding their magnitudes. So we can write ER is equals to E1 plus E2. E1 is equals to E01 sin omega t. E2 is equals to E02 sin omega t plus delta. So let's keep this E01 sin omega t as it is. E02 sin A plus B. So sin A cos B, sin A cos B plus cos A sin B, cos A sin. So what you can take, we can take sin omega t common. So you are left with E01 plus E02 cos delta sin omega t plus E02 cos omega t sin delta. Or rather you should write it a little bit rearranged way. E02 sin delta cos omega t. Now let us put E01 plus E02 cos delta as let's say R cos phi, and E02 sin delta is equals to R sin phi. So what will be the value of ER become? What will be the value of ER under this situation? ER, you see, this will become R cos phi sin omega t. If I take R common, let's say cos phi sin omega t plus sin phi cos omega. So it is not the formula. Is it not the formula of sin A cos B plus cos A sin B? So sin of A plus B na. So R sin omega t plus. So this is the resultant amplitude, resultant displacement. Here we have the unknown terms capital R and phi. These two values we need to find out. So we can say thus the resultant wave has the amplitude R and a phase difference phi. Now to evaluate the value of R and phi, what we can do, we can use these two relations. Okay, so let us evaluate R and phi. So if I take a square on both sides, what we can get? Okay, let's name this equation. 2, 3, 4, this is 5, 7. So we will take square on both sides of 5 and 6. Squaring and adding 5 and you see R square, we take common, cos square 5 plus sin square 5. This is equals to E01 square plus E02 square cos square delta plus 2 E01 E02 cos delta plus E02 square sin square delta. I think you are understanding everything, right? The calculation is just a little bit lengthy, but it is very simple. R square is equals to cos square 5 plus sin square 5 is 1. So E01 square plus E02 square, if you take common, okay, you can see cos square delta plus sin square delta, that is 1. We are not writing it. Plus 2 times 01 E2 cos delta. And that is why you get R is equals to root over E01 square plus E02 square plus 201 E02 cos. Now this expression we get for the resultant displacement, and from this we will easily get the expression of intensity by taking the square of it. Later we will see it is I is equals to I1 plus I2 plus 2 root over I1 I2 cos delta. This way we will get. Anyways, now if we divide equation, let's say 6 by 5, what you get? Equation 6 divided by equation 5, so R sin phi by R cos phi, so tan phi is equals to E02 sine delta divided by E01 plus E02 cos delta. So from here we can get the value of phi, that is tan inverse E02 sine delta divided by E01 plus E02 cos. Okay, this is the value of the phase difference. I hope. So you got the amplitude, resultant amplitude and the phase difference. Is there any question till now or everything all right? Can you move forward? Tell me quickly. We have to go a little bit fast and few. Let me know once it is done, then we'll go for the expression of intensity. So this is the amplitude of the resultant wave. Let's talk about the intensity of the resultant wave. Intensity is nothing but the square of the amplitude, proportional to the square of the amplitude. Intensity of the resultant wave. Okay, we know the intensity of a wave is proportional to the square of its amplitude. Therefore, we can say I1 is proportional to E01 square, right? So we can write K times E01 square, and I2 is also proportional to E02 square, K times E02 square. Therefore, the resultant intensity I is equals to K times R square. You can write K times E01 square plus E02 square plus 1 02 delta. So K times E01 square, that is I1. K times E02 square is I2 plus 2 times root over I1 I2 cos. This is a very important formula. The resultant intensity of the two waves due to interference. So you can see it is the resultant intensity of two waves having intensity I1 and I2. It is not just the summation of I1 plus I2, but it also includes a cross term, 2 root over I1 I2 cos theta. This term is known as the interference term. Okay, we can conclude that therefore the resultant intensity I at any point is not just the sum of the intensity of the two interfering beams. But it also contains an additional term, 2 root over I1 I2 cos delta, which is known as the interface. So because of this interference term, we get the modification in intensity. Variation of cos delta gives rise to the periodic pattern or the wavy pattern. Now we can consider some special cases here. Let's say the intensities of the two waves are same. If the two interfering beams have the same amplitude, what will happen then? E01, E02 are same, let's say that is E0. Then the intensities will also be same, I1, I2, I0. So we can say I equals to root over I1, so I0 plus I0 plus 2 root over I0 cos delta. So you can say it is 2 I naught plus 2 I naught cos delta. So you can take 2 I naught common, right? 1 plus cos delta. 1 plus cos delta is 2 cos delta by 2. So it is 4 I naught cos square by 2. So this will become the intensity if we take the interfering beams to be of the same amplitude. Say one case. So we have just treated mathematically how interference gives rise to this modulated patterns. So if you take two waves and interfere, then we now know how the intensity will be varying. They depend on the phase difference between the two waves. Okay. So let us go for this fringe pattern in Young's double slit experiment. How will be the fringe pattern in Young's double slit experiment? I'm gonna talk about. I hope this is done. fringe pattern in Young's double slit experiment. Okay, so you know the basic setup of Young's double slit experiment. Okay, so in the Young's double slit experiment, you know, from a single source, two coherent sources are produced. Okay, so let's consider the schematic experimental arrangement for Young's double slit experiment. Okay, this is one slit and this is okay. Now we also have screen here. So we have two sources S1 and S2, and the distance between these two sources is D. So D, small d, is known as the slit separation between the slits. You can imagine, look, these slits and this in between thing, these are very small. So slit separation means we are taking the center to center distance, that is D, and a screen is maintained at a distance, let's say capital D. These two parameters are very important. Slit separation between the slit is small d, and the distance between the slit and the screen is D. So you can imagine in this way. Look, obviously this slit is very small, so it's small d. D is capital, means it shows the screen distance from source to screen. It remains in meters. Okay, let's say 1 meter or something. And if you consider this distance small d, it remains around less than 1 millimeter. In that way also you can remember what is small d and what is capital. So two source, let's say one source we are naming as S1, another source is S2. So obviously what will happen, intensity, waves will go from one slit, another wave will produce from another slit, they will interfere, okay, and give rise to bright and dark fringe conjugated. So let us consider a particular point where any arbitrary point, let's say P. So at this point P, will study the interference effect. LL prime is the screen, and the wave which is going from the source S1. So we are denoting it by like this. S2, the light we are showing. So as you can see, the path difference, there exists a path difference between the light which is coming from S1 and which is coming from S2. So because of this path difference, there will be phase difference. Okay, they have been produced from the same source, so they will be having same frequency. This is the one condition of coherent source. What was the another condition? Another condition that they must have a phase difference. As you can see, these two waves reaching this point P, they have this path difference, and path difference is 2 pi by lambda into phase difference is equals to 2 pi by lambda into path difference. So this path difference will produce phase difference, and because of that we get interference. So let's name this point as O, and let's draw to another point, a state point, state here. Let's name them. This is M, this is N, and this point P is situated at some distance, let's say Y, from the midpoint O. So this Y we need to calculate. If you also denote it by Yn, so this shows the nth fringe, position of the nth fringe from the point O. Understood the experimental arrangement schematic? So we have two sources, S1 and S2, both are producing lights of wavelength, let's say lambda, and they are interfering, so there exists a phase difference. So according to the principle of superposition, you can see the net intensity consider. Look, we are not writing anything, just I have just explained while drawing the figure. So just write, consider P as the observation point. This is an arbitrary point, right? So it will be, if you calculate for one point, it will be valid for all the points on the screen. Consider P as the observation point at a distance, let's say Yn, from point O. Okay. So net intensity of light at P, the net intensity of light at point P is given by, we have already calculated, I is equals to I1 plus I2 plus 2 root over I1 I2 cos delta. What is unknown to us? We do not know about delta. Look, let us write the condition for maximum intensity. Under what condition we will get a maxima? Look, this pattern will look like this. If I let's say show you the pattern here, how the pattern will look like. I am just showing you simple example how this pattern will. It will consist of, you see, although I am showing you in a broad way, but this, if you have done experiment, you have seen that these are very finely spaced. You cannot see with bare eyes. We have to use microscope, okay, also telescope to see them. So if you consider it to be dark, then dark, bright, dark, bright, dark, bright, dark, in this way it will be distributed. Okay. Condition for maximum intensity, you know, for maximum intensity, cos delta should be +1. Okay, cos delta should be +1 means delta is equals to the even values of pi. You can write 2n pi. This is the condition where these n's are maybe 0, 1, 2, 3 and so on. This delta is the phase difference, right? So you know a phase difference of 2 pi corresponds to a path difference of lambda. So we know this formula. We know phase difference is equals to 2 pi by lambda times path difference. So phase difference is delta, 2 pi by lambda, path difference is this delta. Both are delta. It is looking like Kronecker delta, it is a delta triangle. So we can say that this delta is equals to lambda by 2 pi times the phase difference. This is equals to lambda by 2 pi. This is 2n pi. So that is equals to n lambda. So this is the ultimate condition. If you want to get a maxima, the path difference between the two interfering waves should be integer multiple of lambda. So this is the condition of interference maxima. This condition is delta is equals to n lambda. Remember this. Delta is equals to n pi and phase difference 2n pi. These two are the conditions. Imax will be I1 plus I2 plus 2 root over I1 I2. So you can write it as root over I1 plus root over I2 whole square. If I1 is equals to I2 is equals to I0, let's say Imax, the maximum intensity will be root over I0 plus root over I0, 2I0, 4 I0. So this is the condition for maximum intensity. Main thing you remember, delta is equals to n lambda, and delta, if you don't remember this also, this is crucial, delta equals to n lambda. This is a condition for maximum intensity. Let's go for the condition for minimum intensity. So the intensity at point P will be minimum. For what value of cos delta? For minimum intensity. Can you tell me what should be the value of cos delta? Should be obviously -1. And cos delta is equals to -1. That is delta is equals to the odd multiples of pi. Odd means 2n plus 1 times pi, where the n can vary like 0, 1, 2 and so on. So this is the phase difference. So what will be the corresponding path difference? Delta. You know, phase difference is equals to 2 pi by lambda into path difference. So path difference is equals to lambda by 2 pi. Lambda by 2 pi times the phase difference. So lambda by 2 pi times 2n plus 1 into pi. So you see pi get cancelled, so you are getting n plus half. So this result is quite important. For maxima, the condition you can see, it is the integral multiple of lambda. For minimum intensity, you see it is the half integer multiple of lambda. If you put n equals to 0, you get lambda by 2, n equals to 1, you get 3 by 2 lambda, n equals to 2, 5 by 2 lambda. So it is half integers of lambda. This is the main condition of interference minima. So minimum intensity, we can easily calculate I minimum, I1 plus I2 minus 2 root I1 I2. That is nothing but I1 minus root over I2. And that is why I was saying that the minimum intensity may not be 0. If I1 I2 are not equal, you see this expression will not give you 0 result. This will give you 0 result only when I1 and I2 both are 0. That is why I said that minima does not mean 0 intensity. Does not necessarily mean 0 intensity. It may be 0, it may not be 0. The special case is if, let's say, both the slits are emerging light waves of same intensity. In that situation, get I minima to be . So if I talk about this, as you can see, for what value of phase difference it is producing the maxima. You can see it is producing for let's say 0, 2 pi, okay, 4 pi, 6 pi, and so on. And here it is producing for, let's say, delta values. Actually these are delta values. Here the delta values are pi, 3 pi, 5 pi, 7 pi, and so on. Okay, if we plot it into a graph, what kind of graph you can expect? Let's say we are plotting this variation of intensity. In this way, we're plotting intensity along y-axis, and we are plotting, let's say, delta, the phase difference between the two interfering waves, along x-axis. So you see, when both I1 and I2 are equal, so let's take the case of I1 equals to I2 is equals to I1. So what kind of distribution you will get? You can see it will give you a maxima here like this, and it will maintain a maximum value. On this side also. So as you can see, the maxima, you try to write the maxima at what values? The what delta values you got the maxima? Got the maxima at 0, 2 pi, 4 pi, 6 pi. 0, here it will be 2 pi, here it will be 4 pi, here will be 6 pi, and so on. Here it is 0, this will be minus 2 pi, minus 4 pi, minus 6 pi. Actually it is you can also add something here. It is plus minus, it also values for it for minus, because cos of minus theta, you know, cos of minus theta, since it is equals to cos theta, that is why if it is valid for 2 pi, it will is also valid for minus 2. Okay, this phenomena we can use. Similar thing goes here. It is a 0 plus minus 1 plus 3 in this. Have I written it correctly or not? ठीक है. And the minimum condition you can see pi, 3 pi, 5 pi, 7 pi and so on. Here it will be minus pi, minus 3 pi, minus 5 pi, minus 7 pi. So this is the plot of intensity distribution in Young's double slit experiment. This is your Imax. For I1 I2 is equals to 0, it will be I naught. Sorry, 4 I naught. Now we need to find out this delta. Is it clear, guys? We need to evaluate delta value. What is delta? As you can see in this figure, delta is the path difference between between the light edge producing from S1 and S2. So it is S2P minus S1P. Okay, let's say, let's name this perpendicular footing. This delta we need to calculate. Okay, so let's do that. We need to evaluate delta. So delta is nothing but S2P minus S1P. Okay, now if we consider, let's say the triangle S2NP. Look at the figure, you have S2NP, S2NP. So this big triangle, as you can see, if this separation is D, what will be this separation? This will be D by 2, right? This will be your D by 2, and this much of separation will also be D by 2. So as you can see, S2N and Pn, y1 plus d by 2 whole square plus d square is equals to S2P square. Can we write it from S2Pn? This right angle triangle, can we write S2P whole square, the hypotenuse, is equals to base is S2N square plus perpendicular NP square. Can you write it? S2N is nothing but the screen distance D, capital D. NP, you see, it is YN plus d by 2 whole square. Similarly, if you take this triangle, let's say S1 PM. So this triangle, if you take this also right angle triangle, so from this what we can write, S1P square is equals to S1M square plus PM square, and PM you can see YN minus D by 2 can write, है ना? Similarly, from the triangle S1 MP, we can write S1P square is equals to S1M square plus PM square. S1M is D square, S1M is D, PM is YN minus D by 2. Can you write it? And hence we can write S2P square minus S1P square is equals to D square is getting cancelled, so you are left with, let's say, YN plus D by 2 whole square minus YN minus D by 2 whole square. Now this S2P square minus S1P square, so A square minus B square formula we can use. And you can see A plus B whole square minus A minus B whole square. So you know a formula, na? 4AB. 4AB is equals to A plus B whole square minus A minus B whole square. So 4AB. Therefore, you see S2P minus S1P. Now S2P and S1P, they are almost of the same order. Okay. You see, the difference between the two slits is very small, as I told you, less than a millimeter. So you imagine it, if you look at some point, let's say from a close distance, this difference is very much pronounced. Now you look at the same thing from a very large distance, it will appear to be that the separation between these 2 points is very small. Are you able to correlate this? You imagine that you are holding 2 ropes, okay, and the 2 ropes are coming from a very large distance and they have some separation. If it is coming from a very large distance, it will appear to be like both of the ropes are having same length. But let's say if you are holding 2 ropes, end of 2 ropes, and the 2 ropes are just little bit away from you, so you will find out a gap, you will find out significant difference between them. But when they are coming from a very large distance, there will be some difference obviously, but those difference will be negligible as compared to the distance involved. Okay, so S2P and S1P is of the same order, we can write them equals to D. So D plus D, 2D. So this is equals to, you see, 2YN into D divided by 2D. So that becomes YN D by, here we have taken S2P approximately equals to S1P approximately capital T. Hence screen is far away from the source. I think using that logic, we are able to write it in and hence we get the formula delta is equals to yn into d by capital. Now we can make use of it. So this will help you to find out the location of the maxima. What we have found out, this is your screen. This is your screen. This is your screen. What we have done, this is your central part. You have done this location, this distance we have calculated, yn. So if you put the condition of delta to be that of the bright fringe, you will get a bright fringe here. So if you put delta is equals to n lambda, you get the position of the nth bright fringe from this point O. If you put delta is equals to n plus half lambda, you get the position of the nth dark fringe. Understood? So what is the location of the nth bright fringe or maxima? Nth maxima, what will be the location? For maxima, delta is equals to n lambda equals to yn d by capital D. Therefore yn is equals to n lambda capital D by small d. This is your location of the bright fringe. So this O point you will get by putting n is equals to 0. The next, after this bright fringe there will be a dark fringe, then again there will be a bright fringe. So that will you get by putting n equals to 1, then n equals to 2, 3 and so on. You will get the position of the bright fringe. So bright fringe also includes the central maxima. This O, at this point O we got the central maxima. So what is the location of the central maxima? Location of the central maxima. For central maxima, you are going to put, you see what is happening at central maxima. Let's take you back to the picture. At the central maxima, what is exactly happening? You see S1 to O, S2 O, and as you can see S1O and S2O both are same. It is symmetrically placed. So what is the phase? What is the part difference? Delta value. What will be the delta value if you consider S1O and S2O? Part difference will be 0. The central maxima is located at the center of the interference pattern. That is at point O. At central maxima, what we have? Delta equals to 0. So let us go for the location of the dark fringe. Location of the dark fringe or minima. Location of the dark fringe minima. So here delta is equals to n plus half times lambda, and that is equals to, we have got delta value is equals to yn d by d, yn d by, here yn will denote the position of the nth dark fringe. So as you can see, yn is equals to n plus half lambda LD by small d. And this gives you the location of the dark fringe. So what will be the location of the first dark fringe? Lambda d by 2d. So you can imagine it in this way. I'm just showing you it in a big way, but these are not so big. These are basically fine lines, but for your understanding, we're showing you in this. So bright, then dark, again bright, again dark, bright, and it will go like this. Just adjust. Let's say this is our central maxima. So on both sides of it, the maxima and minima are symmetrically distributed. Okay. So when you put n is equals to 1, you get the first maxima is n equals to 0, central maxima, n is equals to 3. So these are bright fringe, and if I talk about the dark fringe, this will be the position of the dark. Okay, so this is your n is equals to 0, this is n equals to 1, n equals to 2, and so on. Okay, and you get symmetrically opposite bright and dark fringe. Now what is fringe width? Let's say this is one bright fringe and this is another bright fringe. So this separation is known as the fringe width. Separation between any two consecutive bright fringe or any two consecutive dark fringe. This is known as the fringe width, which is denoted by beta. So you draw it by yourself. I am not a good artist. I have expertise in another art form, not in drawing. Fringe width. You draw the figure as per your understanding. I hope you have understood it. Any confusion is there, you can ask. Fringe width is the distance between any two consecutive bright fringe or any two consecutive dark. Fringe width. beta. Let's say yn plus 1 denotes the position of the n plus 1th bright fringe and yn denotes the nth bright fringe. So beta, this will be the fringe width. Okay, so this is n plus 1, so n plus 1 lambda capital D by small d minus n lambda capital D by small d. So as you can see, it is lambda capital D by small d. So this is the formula of fringe width. Beta is equals to lambda capital D by small d. And interestingly, fringe width is same for whether if you calculate it with bright fringe or dark fringe, this value will be same. You can also check it. Even if you put it here, n plus 1 plus half lambda d by d and n plus half lambda d by, so you will again end up getting lambda capital D by small d. So that is why these widths, these fringe widths, these widths are equal. Okay? These widths are equal. ये वाला कहाँ, तो is it clear till now, guys? Tell me. We are now in a position to tackle problems. Let me give you problems. Okay. इसको कैसे दूसरे पेज पे ले, give it a try. In Young's double slit experiment, light of wavelength 6000 angstrom is allowed to fall on the slits. The fringes of width 2 mm are obtained on a screen. A distance of 1 meter from the slits. What is the separation between the fringe of width means beta value is given to you. Lambda is given to you. Distance of 1 meter, so capital D is given to you. What is the separation between the slits? Small d. Do it quickly. Tell me the answer. Option A, very good. So we know beta is equals to lambda capital D by small d, na? Yes. So d is equals to lambda capital D by beta. Lambda is 6000 angstrom is 10 to the power minus 10. D is 1 meter divided by beta is the width 2 millimeter. 2 millimeter. This will give you 3 into 10 to the power minus 4 meter. This 0.3 millimeter. चलो आगे बढ़े दूसरा क्वेश्चन. What is the separation between the slits of a double slit experiment that gives third order maxima? N equals to 3 at a distance of 8 millimeter from the central maxima. So you can imagine central maxima O, this yn value n is equals to 3. This is 8 millimeter. है ना? The screen is at a distance of 2 meter. D is equals to 2 meter. From the slits and the wavelength uses 500 nanometer. Do it. So what is this 8 millimeter? This is yn value, na? Yn for n equals to 3. Once you know the theory, the problem will appear to be very much easy. Yes, Murli, Harry. Do this one. Write the exact answer you are getting. Exact value of D. What is the answer, guys, for this question? Use your calculator. Here, what is n? N is equals to. What is yn? Yn is equals to 8 millimeter. 8 10 to the power minus 3 meter. D is equals to 2 meter. Lambda is equal to 500 nanometer. 500 10 to the power minus 9 meter. 0.375. Very good. Option A. So we know that the position of the nth bright fringe, it is talking about the maxima. So nth maxima, we know the location n lambda capital D by small d. What you need to know, we need separation D. Okay, n lambda capital D by yn. So all the values are given. N lambda 500 10 to the power minus 9 meter. Yn 10 to the power minus. Calculate, you will get 0.375 10 to the power minus 3 meter. 0.375 meter. Option A. Okay, so let's move on to the next question. similar type of questions. Do this one. What is the slit separation in Young's double slit experiment which produces interference changes 0.1 degree apart on the screen? The wavelength of light is used 589 nanometer. So what is given to us? See, it is talking about something. So we had central bright fringe. Oh no. We had central bright fringe. Then dark fringe. I'm not gonna repeat the mistake. Just showing you few of them. So what does the question ask? The question asks which produces interference fringes of 0.1 degree apart on the screen. Do you understand what is the meaning of? So it is talking about the angular separation of the fringe. I just join the midpoints. The angle it makes, it is 0.1. Okay. I'm giving a hint, or rather note, I should have told you, but you just include this point that the angular separation of the fringe is given by theta is equals to beta on t. So you can understand it very easily. Actually, it is the concept of angle is equals to arc by radius. Theta is equals to arc. Here it is like the radius is d and this is beta. Angle is equals to arc by radius. That is why you get this formula of angular separation. So you can see fringe width divided by the slit distance between source and the screen. Is this thing understood now? And remember this thing, this theta must be taken in radian. You have to express in radian while calculating. Here 0.1 degree is given, but you can just express it in radian while calculation. In calculation, whenever you get this theta thing in your physical science examination, whenever you see theta while calculating, you will have to express it in radian. And you know the relationship between degree and radian. 180 degree is equals to pi radian. Just remember this formula. 180 degree is equals to pi radian. Do it. I think now the question becomes easy. Can you do it? Hurry up guys, hurry up. Do not have all day. We can use the formula of beta, right? Beta is equals to lambda capital D by small d. So beta by d is equals to small lambda by small d. So d is equals to lambda by theta. Not getting my point. Harry, Ajay, Mulli, are you getting my point? Option E. Option A is the correct option. What a coincidence. All the questions have the same answer. Okay. So let's say we know beta is equals to lambda capital D by small d. Now angular separation theta is equals to beta upon capital D. है ना? So we can say that D is equals to lambda times lambda by theta. Lambda is 589 nanometer divided by theta. Theta here, theta is equals to 0.1 degree. So 1 degree is equals to pi by 180 radian. So pi by 180 radian. Just put the value. 0.1 into pi, pi means 3.14 into 180. If you calculate, you will get 0.337 millimeter. Approximately 0.34 millimeter. Tell me guys if this problem is understood or not. Now I think any question if comes from double slit, you can do it. Are you feeling confident? Is there any question till now or confusion till now in understanding or visualizing anything? Or everything is all clear, crystal clear, or clear like water? Did you get the clarity, or is it still foggy to you? This particular topic is very important. Many questions came previously and there is a high chance of getting a question from it in the upcoming exams as well. You must be very clear about these concepts. Should I move forward to the next thing? चलिए आगे बढ़ते हैं. So what are the conditions for sustained interference? The interference pattern must be maintained for quite long. So what are the conditions for sustained interference? Under what condition you will get? Firstly, the first condition is that two interfering waves should be coherent. Coherent includes this same frequency. The two waves should be of same frequency. If the two interfering beings are polarized, they must be in the same state of polarization. What are the conditions for observation? Spacing between the slits D should be as small as possible. That is why you see it is less than a millimeter. The distance of the screen from the two sources should be quite large. That you should have seen it is of the order of meter and millimeter. You can imagine meter is 3 orders of magnitude higher, है ना? 10 to the power 3 millimeter is equals to 1 meter. You can see it is 1000 times large. Condition for good contrast. Contrast means how well you can identify, you can separate between the dark and bright. That is the good meaning of good contrast. Amplitude of the interfering wave should be equal or at least very nearly equal. Then if it is equal, you know, the minima will be completely zero, completely dark. And if it is not exactly equal, the minima will not be exactly dark. The two sources must be narrow. So for this purpose we use pinholes. The two sources should give monochromatic or very nearly monochromatic light. Monochromatic means having a single lambda, or else the part difference should be very small. Now what will happen if we introduce some kind of thin laminar sheet or glass plate in one of the paths of the light beams? So I'm just roughly drawing the figures. You see, we had this scenario, not drawing everything, I'm just trying to show you. So this was the scenario. It was producing interference pattern here, and this distance between these two slits was denoted by small d, and this separation is by capital. Now what will happen? Let's say this was initially the position O, and we got an interference pattern from the superposition of the two waves originating from S1. And now if you introduced a thin laminar sheet here, what will happen? This is a thin laminar sheet. Let's say it has a thickness of P. So obviously the phase difference we measured, S2P minus S1P, that will be changed. For S2P the behavior is not changed, but for S1P, see, the light was previously traveling throughout in air, but now the light is partly traveling in air, mu is equals to 1, and it is partly traveling through this laminar sheet which may have some refractive index, let's say mu. Okay, so because of that, the pattern will remain same. The conjugative bright dark will remain same. Their thickness will also remain same. Only the difference that the overall pattern will be shifted towards the plate. So look, previously if O was the central maxima, after insertion of this plate, overall pattern will be shifted upward. So it will become O prime. Now if you introduce this laminar sheet at the path of the second beam, this O will be coming down. This O prime will be situated on the other side. Remember this one. If it is introduced on the path of S1, the overall pattern will be shifted above O, and if the laminar sheet is introduced on the path of S2, the overall pattern will be shifted downward. This is just you need to remember. Okay, I'm just showing you O. Look, about O we have the symmetrically distributed pattern. Symmetrically distributed pattern like this. For O also it will be symmetrically distributed patterns. It's just that by the introduction of the laminar sheet, the overall pattern will get shifted towards upward. So let a thin plate of thickness, let's say T, has been introduced in the path of light from S1 the refractive index of the plate is mu. Now how much time will it take to go from S1 to P? Now you remember one thing, optical path is equals to geometrical path times the refractive index. This is the formula we to calculate the path difference. We have to use this formula. Optical path, when both waves were traveling in air, refractive index was 1, so there was no issue. But now it is also traveling through this plate which have some refractive index mu, so obviously the path difference will be changed. So to get the path difference between S2P and S1P, we have to find out the effective path difference in air. So we can say, what is the effective path in air from S1 to P? What is the effective path in air from S1 to P? So we can say that S1P is the total path, and you will just subtract the path which has been traveled in this, that is mu minus 1 into. Okay, so before understanding this, we need to understand few more things. Then just a moment. So what is the time taken for the light go from S1 to, you see, S1P minus T, this is the path it has traveled in air. Let's say V0 plus T distance it has traveled, and the effective velocity may be V1. So this is equals to S1P minus T divided by V0 plus V1 is what? You know, V is equals to C by N. Do you know this relation? Speed of light in some medium is equals to C by mu. For air, mu equals to 1, that is why V is equals to C. So this V1 is equals to, let's say this V0 is the speed of light in air. Let's say V0 by mu, and this T. So this is equals to S1P plus mu minus 1 into divided by V0. Or just to remove the confusion, we can just write V0 as C. Actually, why we avoid writing C? Because it is in air. So let's assume that it is vacuum. Okay, free space. Okay, whatever it was. Let's just mention what we have done. V0 is the velocity of light in air. V1 velocity intensity of light in here. The effective path in air from S to P, you can see this is the effective path S1P plus mu minus 1 into T. That is why we have written in this. So at any point P, what will be the effective path difference? Therefore, at any point P, the effective path difference will be how much? Look, S2P, this is not changed. Now S1P, the effective path, you can see it is S1P plus mu minus 1 into T. So it is obviously more than the previous path. So this is S2P minus S1P plus mu minus 1. This was previously denoted by delta, delta plus mu minus 1 into T. So previously, you see the path difference was delta. Now after insertion of the plate, the path difference becomes delta plus some portion mu minus 1 into T. So it's a positive value. Now, if you want to get the location of the bright fringe, what will be the location of the bright fringe? After inserting the plate, location of the bright fringe. So you will just equate for bright fringe, you know, this path difference must be equals to n lambda. For dark fringe, it will be n plus half lambda, n plus half into lambda. So we know the value of delta, that is yn small d by capital D. Just check plus mu minus 1 into T is equal to n lambda. From this, we can get the position, new position of the bright fringe. Yn is equals to, let's take this here, n lambda plus mu minus 1 into T. Have you done any mistake? Acha, यहाँ पे minus था ना, so it will become a minus. That's why your calculation is becoming a bit messy. Why didn't you point out, guys? You are not being attentive or what? I am making a mistake and you are not pointing out. How will it go? Whenever I am making a mistake, you should point out readily. Okay. So n lambda plus mu minus 1 into T we have taken to the right. So what left? D by D. So this will be the new position of the bright fringe. If you want to calculate the bright fringe in this new frame, in this new arrangement, you have to use this formula. लाइफ में कलर बहुत जरूरी है दोस्तों. So in the same way, can you find out the location of the dark fringe? Can you find out the location of the dark fringe? And as you can see, in the absence, you see, in the absence of the plate, absence of the plate means what? T is equals to 0. So when you put T equals to 0, what are you getting? You are getting your old formula back. N lambda D by D, है ना? So what is the displacement of the nth fringe? You see, let me just show you this picture. This was the screen, let's say. Previously, this was your O, this was your O, and let's say this was the position of the nth bright fringe. Nth bright fringe EF. Now, after insertion, this O point has gone to O prime. This bright fringe has also shifted. So this is the new nth BF. Okay. So what is the shift? Shift is this much. So you can see from this figure, if this was your n lambda d by d, this much was n lambda capital D by small d. This much is this n lambda capital D by small d plus mu minus 1 e capital D by small d. So this is the displacement of the nth fringe. Therefore, the displacement of the nth right fringe equals to, let's say we are denoting it by क्या से डिनोट करा जाए दोस्तों? Okay, you can denote it whatever you want, d by d mu minus 1 into, and as you can see, it is independent of t. So it is independent of n. It means all the fringe will be shifted by equal amount. It is independent of n. Hence, the displacement of the nth dark fringe is also d by d mu minus 1 into. Here you can see it just a matter of few things. Location of dark fringe you can easily calculate. Location of dark fringe. Only difference, where only difference will come, you see, you will put then this part difference is equals to n plus half times lambda we will put. So you see your delta is same yn d by d. Okay, your yn will become just I'm just skipping one step. I hope you will not mind. D by d, you see, in space of n lambda it will just be n plus half lambda, and this mu minus 1 into remain as it is, mu minus 1 into t. This will be in bracket. Yeah, this will be the change. So here also you can see that the displacement of the dark fringe is d by capital D with small d into mu minus 1 into. I hope everything is all clear. Let me know if you have any question or your brain has started to hang. In first equation of location of dark and bright fringe location. Oh, here. Very good, Ajay. Mr. Ajay has pointed out a very valid point. Look, यहाँ पे गलती था. That is the mistake is repeated here also. Okay, in both the equations, na? Ajay, thank you. Is there any other mistake other than that? I hope not. Yes. Okay, let's do a problem. In Young's double slit experiment, the slits are at a distance 2L from each other and the screen is at a distance of D. If the glass slab of refracting index mu of thickness D is placed in the path of one of the beams, the minimum value of D for with the central fringe to be dark. Central fringe to be dark, what is the meaning of this? Previously, you see, central fringe was bright. Now, if it after insertion, what is happening? Okay, previously, let's say it had black, then black, then again bright, and so on. So this was, let's say, before. Now you can see central maxima is bright. Now what has been asked? If the glass slab is placed, the minimum value of D for which the central fringe to be dark. Central fringe dark, what is the meaning? It means, you see, the overall pattern is shifted. So central fringe being dark means this black will come here and this bright will go there. That is the meaning, right? The new setup demands this. This is after. So you can see the central maximum has become dark. So how much you need to shift? How much path difference you need to shift maxima to minima? How much extra path difference you need? Isn't it lambda by 2? And extra path difference of lambda by 2 is required to shift maxima to minima. Can you say? You can imagine it in this way: one bright fringe, nth bright fringe. What was its location? N lambda d by d. Have I written? Oh, that's the opposite. Have I written it correctly? I hope so. And you see the dark fringe, the location was n plus half lambda capital D by. So how much change you are doing? How much path difference you require to make this change? Lambda by 2, na? Okay, I think in terms of path difference, if you write for bright fringe, it is delta is equals to n lambda. For dark fringe, delta is equals to n plus half lambda. If you want to switch from bright to dark, how much extra you need to add? Lambda by 2. This is the path difference. Huh? Now I think everything is all clear. If you want to switch from bright to dark, you need a extra path difference of lambda by 2. And we know if you introduced a plate of thickness T, a plate of thickness T, plate of thickness T in one of the paths of the beams introduces an additional path difference of mu minus 1 into T, right? So we can just equate mu minus 1 here. T is given to you D, okay, thickness D. This is lambda by 2. From D equals to lambda by 2 times mu minus 1. Option D. Let me know if it is understood or not. I think it should be understood. Very good question. Number 11. Can we move forward, guys? Should I stop here or should I do a little bit more? Tell me, Ajay, Hari, can you take it more? Or should I stop here? Tell me quickly. Can you take it more? Take it more. Wow. Hello. Let's do another problem then. In a double slit experiment, instead of taking slits of equal widths, one slit is made twice as wide as the other. Then the interference pattern. What changes you will observe in the interference pattern? Okay, let's take this as homework. From a very long days, I have not given you any homework. Take it as a homework. You will think little bit and you will do it. So you can use this. I'm just giving a hint. Your intensity will be proportional to width. Okay, you can use this and you can get the answer. Okay, you will do it at home, and if you can solve it, you can share it, and you can share the solution in the WhatsApp group. Otherwise, I will share the actual solution. Now, what you do this problem. Problem is an easy problem. Do it. In a Young's double slit experiment using light, the apparatus has two slits of unequal widths. When only one slit is open, maximum observed intensity is 4 I0. When only slit 2 is open, maximum intensity is I0. When both slits are open, interference pattern appear on the screen. Ratio of the intensity of the principal maxima to that of the nearest minima. Do it quickly. Could you not find the answer? Harry, Ajay, Murli. You see what the question says? Apparatus has two slits of unequal widths. Only slit 1 is open. You get the intensity 4 I0. Means I1 is equals to 4 I0. Okay. Only slit 2 is open, means I2 is equals to I0. When both slits are open, you get interference pattern. What is the ratio of intensity principal maxima to the nearest minima? Okay, so the ratio it is talking about, you know it, root over I1 plus root over I2 whole square. So principal maximum to the nearest minima is root over I1 minus root over I2 whole square. This was the formula, right? So say square root of 4 I0 plus square root of I0 whole square, square root of 4 I0 square root of I0 whole square. So it is 9 by 1. Is it clear or not? Simple question. Any doubt from this question? I hope not. Chalo, let's go to the next problem. Simple problem. In an interference pattern developed formed by two coherent sources, the maximum and the minimum of the intensities are 9 I0 and I0 respectively. The intensities of the individual waves are, okay, it's just the reverse situation. ये तो prank हो गया. Without solving this question, you can easily say it is B. है ना? I max by I min is equals to root over I1 plus root over I2 root over I1 minus root over I2 whole square is equals to 9 by 1. It means root over I1 over I divided by root over I1 over I2 is equals to plus minus 3. You can take the positive value root over I1 plus root over I2 times root over I1 2 root I1 4 root I2 I1 by I2 by 1 whole square. So that is how it is matching it up. Okay. Only one last problem we'll do and wrap up the session. Interference fringes are seen at an observation plane z equals to 0 by the superposition of two plane waves. A1 exponential this, A2 exponential this, A2 are real amplitudes. The condition for interference maxima is. Can you solve this problem? Superposition of two plane waves. So let's say whatever waves you are given, y1 हम लोग ले लेते हैं a1 exponential I a1 dot r minus omega t, and let's take y2 to be a2 exponential I 2 dot r minus omega t. So using the superposition principle, we can write the resultant will be y1 plus y2. So this is a1 e to the power I a1 dot r minus omega t plus a2 e to the power I k2 dot r minus omega t. No issue till this. Now therefore the intensity of the resultant wave is, you know, intensity I is equals to modulus of y whole square. So it is like y star y, right? because complex quantities are involved, so we have to write it in this way. And if you evaluate this, you will get a1 square plus a2 square plus 2a1 a2 cos k1 minus k2 dot r. Can we write it? What is the condition of interference maxima? The condition for interference maxima is cos of k1 minus k2 dot r. It should be equals to 1. 1 means cos of twice m pi. That means k1 minus k2 dot r is equals to twice m pi. Yeah, cos equals to 1. So it is matching with which option? B के साथ ना k1 minus k2 dot r equals to twice m pi. Yes. Option B is the correct option. So this was a very good question actually. So a lot of things have been done today. In the next class we will be doing a lot of things more. Next class will be on Monday morning, Saturday, Sunday, Monday morning we'll be taking the next session of this interference class. I hope by the next class interference will be over. Okay guys, so thank you very much for joining the session. I hope you find this session very useful and have a great day. Bye bye, take care, enjoy the weekend, bye.